Okay. All right. I think we got things up and running. Let's see. Instead of getting going a little late tonight, we're gonna start a little bit early. Let's see. Let's see how this is going. All right. Get much better highlighter color than this awful weird green we had. There we go. Ooh. It's less of a highlight and more of a very, yeah. That's a beautiful highlight. All right. Sweet. Okay. So if you remember last time, we started talking about Taylor's theorem and power series. This is the build up to the justification for our use of the term analytic. It is where the name here will come from. Uh, so power series, we all know about power series. We've taken calculus too. Just very long polynomials. In fact, so long that they never stop. Polynomials with an infinite number of terms, because otherwise they would just, they'd be polynomials if they had a finite number of terms. And so since they don't, they are power series. It just involves terms, constants times z minus z naught to the n, a big old series like this. Of course, this is defined in terms of limits. We had to talk a little bit in 3.1 about some of the things related to this and limits of sequences, and then get some things about series out of that. We talked a little bit about radiuses of convergence, radii of convergence, the Abel-Weierstrass lemma. We used that to talk about the differentiation of power series, and we got the uniqueness of power series. Now that we've got that power series are unique, at least locally, so that says that this is the last result of last time. We got that power series expansions around the same center are unique. So if you've got two power series expansions around the same point z naught, in some non-trivial disk d z naught r, that is some disk of non-zero radius, non-trivial, then the coefficients of the power series are the same. All right, sweet, that's awesome. That tells us a lot of good things, namely that if we can get a workable formula, then that's the formula. And moreover, if we can find a power series for something, then we will get a lot of information about what the terms of that power series represent. It's, cut to the chase, since you've already seen this basically in Calc 2. The idea is that you form a Taylor series using the derivatives of an analytic function, and this lets you represent it locally, at least, as a power series. And so you can go both ways. If you want to use nice things like Cauchy's integral formula, you can get the derivatives in terms of contour integrals of the function over z minus z naught to the some power, right? That whole business, and you can get power series very easily. Or in the reverse, if you have a power series, you can get information about the derivatives of a function using the power series. So let's start it out, and let's keep it going. So at the end of the last one, we got uniqueness. Now we're going to take a few more things, build up to Taylor's theorem. I will briefly discuss how Taylor's theorem is proved. I won't actually go through the proof because it's kind of long and tedious, and also it'll ruin an exercise that you'll do in homework if I just do it. No, I want to assign it, why not? And then we'll talk a little bit more about some ideas that will come into play a lot more later. The order of zeros and isolation and things of this nature. So started out today with proposition 3.2.6. We will consider a power series of our usual form, the sum from n equals 0 to infinity of a sub n times the quantity z minus z naught to the n. Now, starting with a regular old power series, we have the two following good old tests that you all know and love that we can still use. One, the ratio test. If the limit of, as n goes to infinity, of course, of the ratio of successive terms in the series exists, then it equals r, the radius of convergence of the series. So that is sweet. It says that if you look at, the limit of the quotient of term over next term in terms of the coefficients, then if you get a value out, it equals the radius of convergence. So it gives you a way to calculate the radius of convergence. Kind of nice. So if this exists, and a big old if on that, then it equals r, the radius of convergence for the series. Sweet. All right. Number 2, the root test. We all know and love the root test. The root test looks at a quantity, let's call it rho, which is defined to be the limit, as n goes to infinity, of course, of the nth root of the modulus of the nth coefficient. If this exists, then r equals 1 over rho. This is the radius of convergence as well. Oh, okay, cool. And in this case, we'll, of course, adopt the convention that r is infinity if rho is 0. Since, if you flip that in the limit, right, you would get infinity. All right, cool. Oh, if I didn't say the modulus in this first piece, then I misspoke, but obviously everyone can see it on the screen. All of this is in terms of moduli, so it basically is really just exactly pretty much restating Calc 2 stuff, but we're just pointing out, using our nice little fact from the beginning of this chapter that absolute convergence implies convergence, and so we can bring these things on through. But these remain useful. These classic results, the reason we bring them over, the reason we take them with us into the complex world is because they stay useful. So a couple examples. The series of z to the n has a radius of convergence 1, since an is equal to 1 for all terms. And if you look at the limit as n goes to infinity of an over an plus 1, well, that's obviously 1. It's the limit as n goes to infinity of 1. So it's got a radius of convergence of 1. Okay, cool. It's obviously centered at 0. And this makes sense because anything 1 or bigger in modulus will definitely not converge if you sum it up in terms of its nth powers, right? You take an nth power, second, square it, cube it, so on, right? For something bigger than 1 in modulus, it just keeps getting bigger. If it's smaller, it spirals on into the center there. Okay, makes sense, kind of nice. Similarly, if you're looking at a series whose terms are given by z to the n over n factorial, this guy may seem a little bit familiar, right? This is what? This is exponential, right? This has a radius of convergence of positive infinity, that means it's entire, of course, and an is 1 over n factorial, and so if you look at the ratio of terms, that will be, if you look at the ratio of the terms right there, you can just write this out actually I'm sure everyone sees it, but why is this not working on me? What is going on here? Oh, it got giant. Okay, that's what's weirded me out. Okay, yeah, so obviously right here, this is just 1 over n factorial divided by 1 over n plus 1 factorial, which is just n plus 1 times n factorial, right? And so you just take this division right here, flip it, and so of course the n factorials will cancel each other out. You're just left with an n plus 1 on the top, and you take the limit as n goes to infinity, you get infinity. Cool, easy enough. All right, so that's obviously the exponential function, i.e. e to the c, right? Cool, we know that's entire. We expected that. So similarly, in kind of the opposite direction, instead of dividing by n factorial, if we multiplied by n factorial, looked at the series from n is 0 to infinity of n factorial z to the n, this guy obviously has a radius of convergence of 0, because as you do exactly the same process here, you'll get 1 over n plus 1, and the limit as n goes to infinity, that is 0, of course. So this guy doesn't have has no non-trivial region of analyticity. And we will find out that that means something important later on, at the end of the day. So, kind of cool. All right, back to out of example world. This is back to thinking about proposition 3.2.6 and not just looking at examples using it. Notice we can get r from 2 different ways right here. And it's possible, in fact, in the latter case, to see that rho can be given by this 1 over r as the limit supreme as n goes to infinity of the nth root of the modulus of an. We can actually show that this always exists. So this is a slightly stronger version of the root test. If we don't want to state it like this because I don't know if everyone's seen lim sups or supremums in general. In this case, though, what it means is just going to be the limit as n goes to infinity of the supremum of these c's, right? Cn's, right? Where in our case, since we have finitely many terms in a given for a given n, right? You know, for n equals 1, there's just one term, like the first term, which is the modulus of the first coefficient, and then when n is 2, you know, it's the next one, right? So we just take the max. This might as well just be max instead of sup right here. Nothing too fancy, right? And so it's just going to be the limit of these maximums, and this will always exist. So this is Hadamard's formula. It's worth mentioning because it is slightly better in terms of not requiring these big ifs right here. Because these guys say if it exists, then you're good to go. Hadamard's test, well, we always get Hadamard's formula. We get that these things always exist. So this ends up being a lot nicer in certain ways, but it's not necessarily as easy to calculate. It's just worth mentioning because, you know, Hadamard did some good work. Cool. All right. Now that business aside, if my anticipation isn't palpable, I'm stoked up to talk about Taylor's theorem now because everyone knows Taylor's theorem, and good God, we've done a lot of work to get to a result that we already kind of know. But it's fun. It's a good one, and it is really neat in the complex plane. So Taylor's theorem, stated in its full glory, says that if f is analytic on an open set A in the complex plane, then if we pick some z naught in A and look at a disk of radius little r, an open disk centered at z naught, that is contained in A. So in this case, we just have to make this extra assumption because maybe f is not analytic on the entire complex plane. We're just, you know, saying, okay, we have to look at a disk and we have to make sure that it's inside of the set where f is defined for this theorem to make sense. Don't get hung up on this beginning part or anything like that. But what we're going to say is that for every z in this disk of radius r centered at z naught, the series given by, drumroll, the series that we expect, the sum from n is 0 to infinity of the nth derivative of f at z naught over n factorial times the quantity z minus z naught to the n converges on AR. That is, it has a radius of convergence at least as large as little r, and it equals f of z on this disk. Kind of cool. Okay, this is the Taylor series around the point z naught. Of course, if we set z naught equal to 0 by convention, we call this Maclaurin series for some reason, and because there's a guy named Maclaurin who, you know, was doing stuff with that, but same business, just this nice formula that we all know and love from calculus carries over into the world of the complex plane. How we get there involves some medium tedious calculation at a few points, but is kind of cool. It uses a technique you can describe as integrating term by term, and it justifies a lot of what we did in 3.1 when we talked about when we can exchange summations and integrals in infinite series. We know we can always do that in finite sums, right? So when can we do it in infinite sums? We got ideas about that before with uniform convergence, and it made some sense of why we care about the notion of uniform convergence. Then last time we talked a lot about how analytic functions are guaranteed uniform convergence given some mild conditions, and what we end up doing is we here, I'll even pull something up right here. Let me bring this up right here. Where is it? I was way on a different section. Oops. All right. So we just start out. I'll even grab just. Yeah, here's your textbook. So in their proof, they do a nice little trick using a geometric series. We don't need to focus too much on that or anything like that right now. But basically, the interesting idea is that we're going to use Cauchy's integral formula, which lets us write f of z in terms of this, and then we're going to basically sum up a geometric series, and the manipulations they use to get to it, don't worry, it's not anything too fancy, but just we're going to represent 1 over zeta minus c naught in terms of an infinite series. Okay, it's kind of a dumb trick, but we'll do it, and then we'll use that to grab the zeta minus c naught in Cauchy's integral formula, and we'll use our nice justification for why we can exchange an integral and a summation in this case, and we will bring it on through. That is, we will do some swapping, move that integral inside of the sum, easy, and then we'll use Cauchy's integral formula for derivatives. And next thing you know, you just have Taylor's theorem. It is nothing too complex. It is a useful little trick, though, just to take something in Cauchy's integral formula, write it in terms of a series, then using some good justification to swap out the integral and the summation sign, we'll integrate each term, and then we'll use Cauchy's integral formula for derivatives. And that gives us Taylor's theorem. It's an amazing little factoid, but if you ever see Taylor's theorem, just kind of think of in your head that this is it's basically, the content of it is essentially that of a geometric series. That's how we're, if you think about, like, you've seen like those beautiful little animations where somebody, shows you how a geometric series like fills in a box, right? You start with like little corner, and then you have like a little, here, I shouldn't be holding my hands up. I have a pen, I can draw. You start out going like, oh, I'll do like this little chunk down here, or I should be probably drawing a little bigger than that, actually. I'll do like half the box, right? And then I'll do like a half of what's remaining, and a half of what's remaining, and half of what's remaining, and like half of what's remaining. Like these things, right? Where you kind of like bring it on in, and you get like the area of the box, and like all those cool little tricks for, looking at why a geometric series or some other form of series would converge. Essentially, that is all we're doing when we mess around with Taylor's theorem. We are taking the function itself and we're just breaking apart its values using this geometric series trick. The reason that the derivatives turn up in this case is just because the integral and summation symbol can be flipped thanks to uniform convergence. Hopefully that doesn't make it seem any worse than it is. It is a pretty straightforward calculation. Look in your book, you'll go, oh, it's a cool little trick. There's nothing too fancy about it, and like I said, if we go through and prove it right now, I will ruin a homework problem that I would like to see you do. However, there's a good corollary out of this that we get, and this is where some of the more interesting parts of what we're going to do today start to come up. When you have a region in C, and f a complex valued function. Oh, I still am on my highlighter, good. A region in C, and f is a complex valued function defined on A, good. This is where it's fun. F is analytic on A, if and only if, I'm going to put that in a different color because it's so important. If and only if, for each z naught in A, there is a number r greater than 0, such that the disk centered at z naught of radius r contained in A, such that the disk centered at z naught of radius r is contained in A, and f equals a convergent power series on that disk. That is Analyticity is the same thing. It is continuous differentiability as a function from R2 along with the Cauchy-Riemann equations. These two seemingly unrelated to series representation facts, right? Just like, oh, you can continuously derive, okay, cool, blah, 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 right? And you have this weird little equation, weird. Something about the partial derivatives, That is the same thing as being representable in terms of a series, an infinitely long polynomial, at least locally. That is kind of crazy. That differs so dramatically from the case of real functions. That is a nutso thing compared to real functions. In real analysis, we know that there are functions that don't have nice power series representations. But when you're in the complex plane and you're dealing with complex differentiability and getting all this nice stuff from the Cauchy-Riemann equations, which remember are the progenitor of all of the parts of everything in Cauchy's theorem and all this stuff we've been using. This all comes out of the Cauchy-Riemann equations. The Cauchy-Riemann equations, this little tiny innocuous series of constraints, gives us such a different situation than in the real case. In the real case, you have all sorts of stuff that doesn't have nice representations, but once you go to the complex plane, every single point in the domain of analyticity has a radius about it where you can write your function as a power series. That is cool. That is crazy. That is pretty neat. And it also conversely says that if you can't write your function as a power series for a disk of any radius centered at a given point, it is not analytic there. That's kind of cool. When we're talking about things like, back over here, this guy, right? N factorial z to the n, right? Oh, okay. This guy, just not gonna be analytic. So what is this guy, by the way? N factorial z to the n. Is this? Well, never mind. We don't need to focus on that too much. You might be able to, if you'd like to have a fun exercise, see if you can just use the fact that this is the exponential function to write this in terms of an exponential function, and see if it's something you might recognize from somewhere else. Not worth focusing on right now, but it also gives you a way to disprove analyticity without even having. Think about the fact that the Cauchy-Riemann equations require you to find partial derivatives and set things equal, and they have to match up. So you have to maybe do some difficult computations to figure out if that's the case, right? It is enough to represent something as a power series to know that those equations hold. So, for example, if you're trying to find a harmonic conjugate to make, to make yourself an analytic function, that is, you're trying to solve some partial differential equations that maybe are a little bit tricky, you can do it even without actually doing it, just by finding a series representation. It's kind of cool. Finding series representations is enough to solve certain partial differential equations. It's crazy. Maybe not if you've, that's actually something we often do, but on its surface at least, it seems a little bit weird. This fact right here, this corollary, is the neat thing about Taylor's theorem to me. It is just, it really just shows how wildly strong the mild constraint of Cauchy's equations are. Satisfying that gives you so much. It is probably the most outsizedly powerful result in all of mathematics. That's how I kind of think of it. Is lots of other theorems, you have to assume all this stuff, and then you get back something that's about as strong as the amount of things you had to assume, right? You make some pretty heavy assumptions and you get back some pretty heavy results, or you make mild assumptions and you get back a little bit, not that much. But the Cauchy-Riemann equations are nuts. You go well, assume you satisfy two little tiny equations, so they're not even anything, right? And then bam, like this entire class comes out of it. It's nuts. And we're not even going to go that deep into complex analysis. It is kind of like, you know, I don't know, it's like mathematicians are like planting some seeds, and you know, you're growing like regular old plants. Occasionally you plant a seed and you get like a tree out of it, and you're like, cool. And the Kosher Riemann equations, you know, you planted it in like it's like a freaking redwood, you know. It's like this like massive like titan of a thing. It gave an entire discipline out of it. It's kind of nuts. So if you proving this obviously is it's been on screen for long enough now that I'm sure everyone's read it. But Taylor's theorem, if you want to prove this, Taylor's theorem shows that every analytic function is equal to a power series. In fact, it's Taylor series, obviously, on every disk in its domain of analyticity. Cool, easy. On the other hand, if f of z is equal to a convergent power series on a disk of radius r centered at z naught, then this disk centered at z naught of radius r must be in the interior of the circle of convergence of the series. Okay, yeah, we know that, right? We did that. I mean, that just is obvious and kind of tautological, right? If it converges, then well, it must be in the radius of convergence, right? If it didn't converge, then it wouldn't be, but it does. So we're in the radius of convergence. But the cool thing we did last time is that you get analyticity from this. That's pretty cool. Okay. Since there is a disk like this, though, and a convergent power series for each z naught in A, it then obviously follows from the analyticity of power series that f is analytic on A. Oh, okay, cool. Well, basically it just says, hey, power series are analytic in the region of convergence. So if you can write a function as a power series, you obviously, you know, retain that analyticity on that region. Easy enough. These are just long polynomials. So that direction is not weird at all. Polynomials are obviously analytic, and so very long polynomials, if they retain that property at least locally from polynomials. They may not be entire, but they at least locally retain this analyticity. All right, easy enough. And that's pretty cool. The next consequence, though, and I'll stop just absolutely rambling about how cool I think this Taylor's theorem is in the context of complex analysis, even though it is really cool. And we can talk a little bit about isolated zeros and oops, get rid of that. Isolated zeros and the order of zeros and what all this business is about. So I think that the way to talk about it is just this. So when we've got a power series, we're writing f of z in terms of a sum from k equals 0 to infinity of the kth derivative of f at some point, let's call it c, over k factorial. We've been using n so far. I hope it doesn't throw anyone off to use k's instead, and we're using c's instead of z naughts. Who cares, right? When you write a function in terms of its power series, obviously these terms right here will determine what things are 0 and non-zero in this expansion, right? What pieces in this sum are 0 and non-zero. That is, if you're not plugging in a value, right, if you're not plugging in c yet or anything like that, the only way that some z minus c to the k will not appear for some value of k is if you have a 0 for fk, the kth derivative at c, right? Obviously, if you plug in c, you'll get out 0. I'm not talking about the value of f of c right here. However, that does play into, here's what I'm trying to say. If the kth derivative at c is equal to 0, think of it like this. I was going to write for k in the naturals. But I don't know if we feel good about that for all k, right? If this is the case, then we obviously have that f of z is equal to 0 on a disk of radius r centered at c, right? That makes sense. That is, if every term in this power series is 0, then obviously on the radius of convergence, it is 0. Okay, that's fair. That's fair. If not, then there is a smallest value of k for which the kth derivative of f at c is not equal to 0. i.e., if k equals 0, then the kth derivative of f at f of c is not equal to 0, right? If so on and so on and so on. If k equals n greater than 0, then we're saying, like, f prime of c, or f to the n minus 1, the n minus 1th derivative of f at c equals f to the the n minus 2nd derivative at c equals so on, so on, so on, down to f prime at c and f of c. These guys are all 0, right? What I'm saying is that everything, if it's not 0, then there is some smallest value of k where you start picking up terms. That is, if you actually wrote this out, what is the first term in terms of this piece right here? When do you actually have one of these pieces? Something you might ask. It's not an unreasonable thing to ask. All right. This tells us this is, here's the way to think of it. The terminology here that we use is we say that f has a 0 of order if it's n right here, right? We'd say that f has a 0 of order n at the point c, right? Maybe I should have used a different point than c. I don't know, whatever you want. The kind of idea about it is, I mean, if you look up here, I know I said here, like, oh, if it's like, like 0, if it's fc is not equal to 0, but look, it goes 0 right here, Obviously, you plug in c into a power series centered at c, you're going to get 0 out, right? So this is going to give you, you plug in everything except maybe the first term, right? Will give you 0. And so if you have if you have f of c equal to 0, then this whole thing gives you 0, right? But maybe f of c isn't equal to 0, and so this k is a 0, and so you have 0 to the 0, that would be gone, right? Okay. That aside, just in case anyone is thrown off by that, having a 0 of order n at a point c just means that the first n derivatives are equal to 0, and they don't pop up in the series expansion right here. Why would we care? Well, just think about the fundamental theorem of algebra. I'm going to try to kind of write in a different color. I should have given myself more space right here. I've been worrying about that right now. If f of c equals 0, or I'll even write it like this. If you have a polynomial, right? If p is a polynomial, and p of c equals 0, then z minus c is a factor of p, right? If you have a polynomial and you plug in a value and you get 0, then z minus c is a factor, right? Assuming the polynomial is a polynomial in z, of course, right? Okay. Now, just example, kind of think of, say you had p of z equals, like, I don't know, z minus c squared, for example. Obviously, this has z minus c as a factor. Notice if you take a derivative here, p prime of z, well, we'll get 2z minus c, right? Okay, nothing fancy there at all. Easy enough. Now, this business very obviously still has z minus c as a factor, right? So the first derivative does. Oh, but as soon as I take another derivative, I get down to just 2, right? Oh, it looks like there's 3 primes right there. I think my pen skipped. Double prime. There we go. So you get down to just 2 right there, right? And now z minus c is no longer a factor, right? There's nothing fancy there. That's just a very obvious thing. That's the order or multiplicity of, right here, of a 0, right? Now, if you think about Taylor series, power series as very long polynomials, some notion of this is carrying over, right? That is, having a 0 of order 2 for a polynomial means that there's 2 copies of that 0, right? Of multiplicity 2, right? Okay. Now, how about in a power series? Well, when you have a non-zero term in a power series, one of these guys is non-zero, then you pick up z minus c to that power in your sum. All right. But you also pick that up in every term thereafter. That is, and I'm gonna probably give myself a little bit here. I'm actually gonna give myself a tiny bit more room here and erase a bit if that's acceptable. I'm gonna erase this a little. I normally try not to erase since I do a digital canvas and I can really give myself as much room as I want, but I've already started, so I might as well finish it. Oh, my poor little dude upstairs, if you can hear him, he's having a bad night. The little guy is teething, and he is not too happy about it. Anyways, so if you're looking at a power series, actually, let me give myself even more room and just take off this fragment of a sentence here as well. If you have a power series that looks like this, right? If fk, the kth derivative at c equals 0 for k equals 1, 2, all the way up to, say, like n minus 1, right? If it has a 0 of order n minus 1 there, right? Then f of z equals the nth derivative at c over n factorial times z minus c to the n plus the n plus 1th derivative at c over n plus 1 factorial z minus c to the n plus 1, and so on, right? Forever and ever. If you accept me writing this sum as with the dot dot dots, right? Notice I can pull out the z minus c to the n, right? So z minus c to the n, and then I'm going to put in big parentheses, I just have the nth derivative right here over n factorial plus n plus 1th derivative at c over n plus 1 factorial, and then z minus c plus, and so on. And hey, wouldn't you know it, what I have is I have z minus c to the n times the sum from k equals 0 to infinity of f to the n plus k, kth derivative at c over n plus k factorial times z minus c to the k. Hey, how about that? Look at that. Now notice I can, just by doing a little bit of manipulation right here, I could write this as n factorial plus blah, 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 down to the k factorial, right? I can extract the k factorial from this. There's just a whole bunch of extra multiplication stuff in front of it. It looks a little messy if you write it like that. And what I've obtained is I've obtained another power series. Oh, okay, cool. And I've extracted this as a factor. Exactly like I can extract z minus c as a factor from a polynomial that has c equal to 0. I can also extract it from the derivatives and so on, right? So this is kind of cool. It's pretty obvious if you just bring things out. It's nothing remotely fancy at all. All that's going on is that when you have the first kth derivative, or first n minus 1 derivatives equal to 0, when you get to the nth, that tells you that z minus c to the n is a factor of f of z in terms of its representation as an analytic, or as a series at a given point, or if we're just starting with the series, it has that as a factor. And this is kind of cool. What it means is that you can take an analytic function and near a 0, right? You can write it as z minus c to the n, and then some other analytic function which is not 0, since this little chunk right here is not 0, right? Plug in c to, let me use a different color to make our lives easier. This little guy right here, plug in c for z. Then everything after all this will go away. But this piece right here is non-zero because we assumed that, I should say, if that's the case, and I should say the nth derivative at c is not equal to 0, right? I mean, I said that out loud, but to make that clear, this piece right here, we're assuming is not 0. If you have a 0 of order n at a given point, then you can write your function as z minus c to the n times some other analytic function using this theorem right here, corollary 3.2.8, corollary, not theorem, since it's, it's got a series representation, it's analytic, okay, which is non-zero at that point. That is, you can take a function f of z with a 0 of order, an analytic function f of z with a 0 of order n at a given point, and write it as z minus c, that point, to the n times some function phi of z, where phi is analytic and non-zero at c. Kind of cool. It's just like the factorization we're doing here with the polynomials. It's the same business. Moreover, if with a phi of c not equal to 0, right? This is the statement. If f of z has a 0 of order n at c, then you get this. And conversely, that's what this means in a certain sense, is that you can write f of z like this with phi of c not equal to 0 and phi analytic. So you have an analytic function with a 0 of order n at a given point. Then you can factor that guy like a polynomial with another analytic function that is not 0 at that point. Kind of cool. A consequence of this is that the zeros of analytic functions are isolated in the same way that the zeros of polynomials are isolated. That is, they occur by themselves. They're not exactly next to another 0. Let's state this better than my messy handwriting right here because I didn't give myself enough room. So the proposition that I'm alluding to is proposition 3.2.9 in your textbook. Here we start with f, an analytic function from omega to c, where omega is an open set, and we take some point C in omega, then we look at the disk centered at C of radius r. This is an open disk centered at C, contained in omega, the domain of F. It's part of where it's analytic, and we're going to suppose that f of C is equal to 0. That is, that it's 0. Then one of two things must occur. The first option is that F is 0 on the disk. Nothing fancy there. The second option is that it's not 0, right? And for some number n, you have the first n derivatives equal to 0, and finally one of them not equal to 0. So if it's not 0, then, you know, since we have to have a series representation of this form, at least one of its derivatives at that point must be non-zero. Okay, so you get the first one that's non-zero. In the latter case here, where this happens, there is some function phi of z, which is analytic in the same disk, is not equal to 0 at that point, and is such that f of z is equal to z minus c to the n times phi of z for all z in the disk. And there is some radius rho such that f of z is 0 only at C in the disk centered at C of radius rho. Essentially think of it like this, since we're breaking down our function f here as f of z equals z minus c times phi z, right, phi of z. This guy, if it's not equal to 0 and it's analytic, well, it's, I mean, we know what it is. We've written it out over here, right? This guy is obviously continuous, right? So if it's non-zero at a point, then it's non-zero very close to that point. So obviously, if it's not 0 at C, then you can get some little tiny disk around it where it remains non-zero, right? And that is the gist of it. The corollary, the way of saying this this idea that there's a radius rho such that f of z is 0 only at C in this disk, is to say that the zeros are locally isolated, sort of, right? If you have an analytic function on the same domain, same setup, analytic open set omega in the complex plane, C a point in omega. The way of thinking about this is that if you have a sequence of distinct points in omega that converge to C as k goes to infinity, zk's that go to C as k goes to infinity, and f is 0 at all of these zk's, then f is 0 on the largest open disk centered at the point C contained in the domain of analyticity. Huh. That's nuts. That's kind of cool. That is a wild thing. If you can find a discrete, you find the sequence of points, like not even some like continuousy thing. It's just like just, you know, these little dots, right? Going towards a point, and an analytic function is 0 on all of those points, then it is 0 on an entire open set. That is a crazy local to global kind of thing, right? It's not even just the case that, like, oh, I can grab, you know, I got like a point C, and, you know, if I, you know, 0 of order n, blah, blah, you know, I can get some, I have my disk of radius r, and then I have like my disk of radius like rho around C, right? It's not just a case that it's going to be 0 in here, but if I can find any sequence of distinct points that converge to C and on which f is 0, then f is 0 on an entire disk, not even just on someone inside of it, but on the largest open disk centered at C contained in the domain of analyticity. Kind of nuts. Not only do these zeros have to be like the, you know, not only does this is an immediate corollary of the previous one if you think about it a little bit, but if your intuition says, hey, look, oh, you've got phi, you know, analytic, and it's non-zero. Oh, okay, well then, you know, we get some radius where f of z is 0 only at the point C on this disk, right? Well, you might think like, well, this means that I can always get some like very, very tiny disk that, you know, it's non-zero on. And that's true. That's absolutely true. But think about this. If you have any sequence of points in omega that goes to C, then, well, some all but finitely many must be in such a small disk, right? And so you might as well just be working in this disk in the first place. And so basically it says that you can just restrict to this little piece, and oh hey, if I'm going to 0, then I can't have that situation happen where I'm non-zero near it, because any sequence that converges to C must have all but finitely many points in a disk of small radius nearby. But hey, we've got that it's non-zero on such a disk. Huh, kind of weird. Kind of crazy. Anyways, I'm kind of babbling, and my poor long-suffering wife has been comforting our fussy infant for too long. So I'm gonna go help out, and I think we have homework student night. We do have homework student night. I don't think so. I know we do. If you have any questions, please shoot me an email. I will check that. I haven't gotten any emails recently with questions, so hopefully everybody is doing well. I'm getting through your exams. I just got back last night from my trip. I'll hopefully have those to you pretty soon here. It's going pretty well so far, actually, I'd say. Everyone, good show so far. Right on. Anyways, I better get to it. Have a great night.